friends, this video will help you understand the Ohm's law, which describes the relationship between voltage, current, and resistance. Let us begin by stating the Ohm's law that was established by George Ohm. It states that the current flowing through a conductor between 2 points is directly proportional to the voltage between the 2 points and is inversely proportional to the resistance between the 2 points. In order to visualize this concept, let us use the water analogy. Consider a tank filled with water. Now, let us connect another empty tank to it using a pipe. The water from tank 1 will start flowing into tank 2 because of the difference in water pressure between tank 1 and tank 2. Thereby, tank 2, which was empty while it was getting connected, would now get filled up. This will happen till the water pressure between both the tanks is equalized. Here, we can consider that the water pressure is actually equivalent to the voltage and the flow of water is equivalent to the current. The thickness and the length of the pipe here would act as the resistance. Let us look at the different cases in water analogy as well as in electrical environment with the help of the PhET Interactive Simulation so that we get a clearer picture of the concepts of voltage, current, and resistance and the relationship between them. In the first case, here, we can see the two tanks, T1 and T2, and the scenario is slightly different than the previous one in the sense that T1 is now slightly higher in level as compared to T2. Say I increase the height of tank T1 by h. Here, what happens is the water pressure of tank T1 goes higher up because the potential energy of the water in this tank is increased. So, because the water pressure goes higher, the flow of water from tank T1 into T2 increases. So, here we can see that with the increase in height, there is an increase in water pressure, which leads to the increase in the flow of water from tank T1 into T2. We can consider the same scenario in the electrical environment. This is the PhET Interactive Simulations environment. The link for this website is shared in the description. So here, I'm going to consider that the resistance is fixed, say around 200, and I am going to just change the voltage. So if I increase the voltage, meaning if I increase the water pressure, the amount of current which is going to flow through the conductor is going to increase. So here they are considering that every battery is 1.5 volts. Greater than that, another battery is going to get connected in series. So as we increase the voltage or as we decrease the voltage, the current flow through the conductor also increases or decreases respectively. So we can see that the voltage and the current are directly proportional to each other. All along, we did not consider the thickness and the length of the pipe. Even in the electrical scenario, I varied only the voltage. I did not disturb the resistance. Now, we are going to consider the effect of the thickness and the length of the pipe and how it is going to alter the flow of water from tank T1 into T2. So here again, we have tank T1 and T2 and the height has not been changed. It is kept at h. So this remains h. But what has changed is the thickness. So if I change the thickness or I increase the thickness, then what happens is it allows more water to flow through the pipe into tank T2 and T2 gets filled up faster. So here the thickness is increased, meaning it leads to an increase of flow of water. In the electrical environment, we can therefore say that if the area of the conductor or the thickness of the conductor is increased, then the resistance that it offers decreases, which in turn leads to an increased rate of flow of charge or increased amount of current flowing through it. Let us look at the next case. Here, if the thickness is kept the same but the length of the pipe is decreased, then the time that it takes for tank T2 to get filled decreases. This means that the flow rate has actually increased. Flow rate here again is analogous to current in the electrical environment. So we can say that if the length of the conductor is decreased, it leads to a decrease in the resistance. Therefore, there is an increase in the current. So let us look at the relationship between the resistance and the current in the PhET interactive simulation environment. So here I am fixing the voltage at 5 volts and I am varying the resistance. When I increase the resistance, it is seen that the amount of current that is flowing through this conductor or this resistor decreases. When the value of resistance is decreased, the amount of current through it flowing through it increases for a fixed voltage. So we can see that the relationship between the current and the resistance is in an inverse manner. Now, in order to understand the concept of resistance, let us consider that there are a few pebbles that have been placed within the pipe. So we can say that the consistency of the pipe on a whole has changed. So the effect on flow rate would be that the amount of water flowing through the pipe from T1 into T2 would be slower. So the flow rate actually decreases because there is an increase in the resistivity of the material that the pipe is made up of. So here again, we can relate this to the electrical scenario. If the resistivity of the material increases, then the resistance that it offers increases, causing the amount of current that is allowed to flow through it to decrease. So, to summarize the parameters that the resistance is related to, we see that with the increase in area, the resistance decreases. With a decrease in length, the resistance decreases. And with an increase in resistivity, the resistance increases. We can now establish the relationship between the parameters that resistance is associated with. So here, R is proportional to the length, it is proportional to resistivity, and is inversely proportional to the area. So here, resistivity being a constant for a particular material, we can consider it to be the constant of proportionality. So R is given as rho L by A. Here, we are now going to vary the resistivity. So that actually changes the nature of the conductor. So if resistivity increases, the resistance increases. Similarly, let's fix the resistivity. If we increase the length of the conductor, the resistance of the conductor will increase. If we fix the length but we alter the area, if we increase the area of the conductor, then the amount of charge that it can hold between 2 points and the amount of flow of charges between 2 points increases. So therefore we can say that the resistivity or the resistance that it offers to the path of charge actually decreases with the increase in area. So this again is available in the PhET interactive simulation environment. You could explore it and find out more. In order to summarize, we can now consider the water pressure in the water analogy to be equivalent to the voltage of the electrical scenario, the flow rate to be equivalent to the current of the electrical environment, and we established the relationship between the voltage, current, and the resistance as the current being directly proportional to the voltage and inversely proportional to the resistance of the conductor between 2 points on the conductor. Here again, we also saw that the resistance is actually proportional to the resistivity rho, inversely proportional to the area of the conductor, and directly proportional to the length of the conductor, thereby giving us two very important formulae. I is equal to V by R and R is given by rho L by A. The units of current here would be amperes, the voltage is volts, and the resistance is ohms. We can actually work it out and see that the unit of rho is given as ohm meter square by meter, therefore ohm meter. So these are the units and the corresponding symbols of the various electrical parameters, the Ohm's law, and the relationship that could be used to find out the voltage, the current, and the resistance. So if you have any unknown in your given problem, for example, if you want to find out V, you can use IR as the relationship to find out V. If I is the unknown, you can find it out as V by R. If R is the unknown, we can find it out as V by I. If V and I are not given, but parameters like resistivity, length, and area are given, in that case also, R can be found out as rho L by A. Thanks for watching this video at the 11th hour. Please subscribe the channel for more such videos.